Good morning, everybody. Today I will show you some applications related to the use of satellite rainfall data for landslide risk assessment. Let's start saying that landslides are one of the most common and dangerous natural hazards, causing every year several damage and loss of human lives. In this figure, you can see the spatial distribution of landslides and their impact in terms of fatalities, related to the size of these circles, during the period 2007-2017. More than 10,000 events have been recorded throughout the globe, so it is important to provide useful tools for the mitigation of such events. Generally, to mitigate landslide risk, countries have developed early warning systems based on the rainfall threshold. Here you can see the main features of present and past early warning system for landslides throughout the globe, reported in this study by Italy in 2020. And we can see that many of them are still in development or they are not operational. And they, of course, as you can see, they are not distributed uniformly throughout the globe. And they are mainly based on rainfall threshold based on observed rainfall through a monitoring network, so through rain gauges. I don't know if you are familiar with the concept of rainfall thresholds, but basically they are empirical relationships that are defined as the best separators of the rainfall condition that resulted or did not result in the slope instability. As for instance, in this example, it is reported an ED threshold, so accumulated rainfall and rainfall duration threshold, in which we can set all the rainfall characteristics of a rainfall event, in this case the duration and the total amount of rainfall fallen during the storm. And if the point falls below the threshold, we can see that no landslide will be triggered. On the other hand, if the point falls over the threshold, we will likely have a landslide. In this slide that probably you have seen yesterday during the presentation of my colleague Christian Massari, we can see the spatial distribution of the rain gauge stations throughout the globe. And we can see that they are not distributed in a uniform way throughout the globe. There are many areas with just a few or no rain gauges. So it is important to underline that the use of rain gauges for rainfall monitoring related to the use of rainfall threshold is not applicable everywhere in the world, because we don't have enough information to develop a rainfall threshold. Despite the great availability of satellite rainfall product with the global coverage, high spatial and temporal resolution, and obtained by classical retrieval approaches, or for instance, obtained through the SM-to-rain perspective, so the bottom-up approach. The use of these products for landslide risk assessment and related applications are still very rare. Here, for instance, we have an example of the global landslide hazard assessment for situational awareness, the global LASA model developed by Kirschbaum and Stanley in 2018. Basically, the model combines high resolution susceptibility map, as you can see here in the left part of the slide, at the high resolution, as I was saying, at 1 kilometer of spatial resolution, with an antecedent rainfall index based on GPM rainfall data. According to the amount of this index if is above or below a certain threshold, the model issue an outcast according to the degree of susceptibility of the selected pixel. But are there any other ways in which we can use satellite rainfall products for landslide forecasting? To answer this question, we considered a catalog with my colleagues in Tirti of more than 2,000 rainfall-induced landslides occurred in Italy during the period 2007-2017. And here you can see how the spatial distribution of the landslides, and we can see that they occurred basically everywhere in Italy, so it's a very hot topic for us. And we test the capability of 4 different satellite rainfall products. Basically, we test the performance of SM terrain derived rainfall, 2 top-down products, namely the 3B42 real-time stream product and the GPM yearly run product. And then we test also the beneficial effect of integrating bottom-up and top-down approach through the use of SM terrain rainfall estimates and 3B42 product. As you can see here, all the products have been regraded over a common grade of 10 kilometers, grade with a spacing of 10 kilometers. 10 kilometers, yes. To test the capability of this product, we construct the ED thresholds for each satellite product by using an algorithm developed by Melil et al. In which we are able to reconstruct, as you can see here, several to extract from the rainfall time series different rainfall events. In this way, we are able to identify the rainfall events that likely trigger the landslide, and we are able to estimate the total amount of fall rainfall and the duration of the storm that likely triggered that landslide. And we build up to several rainfall thresholds according to different non-exceedance probability level, as you can see here, for different non-exceedance probability levels, as I was saying. For each threshold and for each satellite rainfall product, we estimated the number of the true positive, the false positive, the false negative, and the true negative values in order to assess the quality of the performance of the satellite rainfall product. Here you can see the 4 thresholds obtained for the product at a non-exceeding probability of 50%. With the related values of the score I was saying before. These values allows us to estimate the rock curve for each product, and we can say that the closer is the curve to this perfect classification point, the better are the performance of the selected product. And here we estimated the probability of detection, the probability of false detection for each non-exceeding probability, as you can see here, and for each satellite rainfall product. And we can see that SM terrain as calculated rainfall performed the best among the satellite rainfall products here we have considered. These results confirm the capabilities of satellite rainfall product to be used for this kind of application, even in countries with a dense monitoring network, like for instance in Italy. We perform a similar study in India by considering a catalog of almost 200 rainfall-induced landslides occurred during the period 2007-2019 by considering 4 rainfall products. Basically, we consider the IMD, that is a gauge-based product available over India, with a spatial resolution of 0.25 degrees. Then we test the capability of GPM yearly run product. Of course, we test also the capabilities of SM terrain derived product over the study area. And then also in this case, we integrated the 2 products to obtain 4 data sets. Here you can see, by applying the same procedure I was describing before, we build up the rainfall threshold, and we estimated the values of the probability of detection, the probability of false detection for each analyzed product. And here you can see the curve. And here you can see better, probably you can see better the area under the curve, so you can see how the product performs with respect to each other. And we can see that the integrated product emerge. Here you can see the light blue area is the closest to the perfect classification point. So basically, we can see that all the satellite rainfall products perform better. I'm sorry, with respect to the gauge-based product that is represented by this yellow area here. So these results confirms the added value of using the satellite rainfall product for this kind of application. Also in the case of not so dense monitoring network. Then we test also the capabilities of satellite rainfall data to be used in forecast model characterized by very high spatial resolution. To do this, we take advantage of a new soil moisture dataset obtained by integrating the Sentinel-1 and SCAT soil moisture data, which is called SCATSAR. And the integration is able to provide us a soil moisture dataset with a spatial resolution of 1 kilometer, so very high spatial resolution. By applying EUMeTrain, we are able now to obtain a rainfall product characterized by a daily temporal resolution and 1 kilometer of spatial resolution. So it's characterized by very high resolution. And here you can see the comparison of the spatial pattern between the rainfall obtained through the application of EUMeTrain to SCATSAR dataset here on the left, and the observed dataset obtained through the monitoring network over Italy. And we can see that the satellite rainfall product is able to represent the observed situation and by showing similar spatial patterns. We apply this data to a model that basically use a lot of parameters. Is a data-driven approach. Here, for instance, you can see all the static parameters that we use. Basically, we use a digital elevation model with 5 meters of spatial resolution to extract several terrain features. And then we use also, of course, some dynamic parameters, like, for instance, rainfall time series and soil saturation maps obtained through the use of ASCAT and through the use of, for instance, for Sentinel data. And we use this data to test and to estimate the temporal probability of occurrence of shallow landslides in over a steady area located in northern Italy. We have done this in the framework of a national project named Andromeda, funded by Fondazione Cariplo. And here you can see one of the basin of the study area during a rainfall event occurring in April 2009. And here you can see the probability of occurrence of landslide. I know that probably you couldn't see well, but here you can see that basically on the 25 of April, the basin is basically completely green, so it's characterized by a low probability of occurrence, while on the other end, 2 days after, we can see how the study area is characterized by the presence of high and medium-high areas that is characterized by higher probability of occurrence of landslides, and how the blue dots that represent the recorded landslides fall within this area. We have done this by using both gauge data and soil moisture derived rainfall, of course. And we can see that also in this case, soil moisture derived rainfall or satellite rainfall product can provide reliable information. Here we test we validate the procedure by using by considering another rainfall event in November 2011, and here you can see how the black dots that represented the recorded landslides well fit within area characterized by high probability of occurrence. So also in this case, we have seen that the proposed methodology is able to assess the landslide risk also at high spatial resolution, also by considering satellite rainfall and soil moisture data. The last application I want to show you take advantage of the experience we had in Umbria, in my region, here in my region, and there the Civil Protection Service, in collaboration with IRPI, with us, build up an early warning system that is based on a set of thresholds, as you can see here, that takes into account soil saturation and the cumulative rainfall over an analysis grid set up over the region. The soil saturation conditions are estimated in an operational way every hour through the use of an hydrological model. As you can see here, the green lines represent the soil moisture time series for each grid point, while the blue line represents the spatial average. And also the soil moisture condition are also monitored through the use of HSAF soil moisture product over the region. The rainfall thresholds are built up by considering historical events. So basically, the civil protection operators took the soil moisture at the start of the rainfall event and then estimated the total rainfall that likely triggered the landslide. And by using some meteorological forecast, for instance, here we can see the weather forecast obtained through the ECNWF. They are able to estimate if one of the grid points is overcoming or not the threshold, and then they can issue some alarms related to the overcome of that point. And we have performed something very similar over Italy. In the same way they define their threshold, we consider a catalog of more than 1,000 landslides occurred in Italy during the period 2007-2014, and we use ASCAT soil moisture products to define the soil saturation condition that are represented here by the red dashed line. Here we have the day of occurrence of a landslide, so we take into account the value of soil moisture at the beginning of the storm, right? And here you can see the rainfall time series. So we consider the total amount of rainfall fallen during the storm event that likely triggered the landslide. In this way, we are able to define for each analyzed landslide these satellite soil moisture cumulative rainfall couples to fill this graph, and we are able to define a preliminary rainfall threshold, in which we can see that how in drier condition required a larger amount of rainfall with respect to wetter condition to trigger a landslide. So in this way, if we know how much water is stored into the soil by using the satellite soil moisture product, and if we know how much does it rain over the study area, we are able to know the position of the point of each grid point over the study area with respect to the rainfall we have obtained through after the analysis of the historical event over Italy. And then we are able to know how much water is needed for the occurrence of landslide over a specific point. So we can compare this, let's say, one-day landslide guidance with weather forecast in order to issue an alarm. but this is a very still a work in progress. So we are expecting to obtain better results in the future. So in conclusion, satellite rainfall products that have been considered in this presentation and these studies are able to predict landslide occurrence in Italy and in India through the use of different methodologies. As we can see, we have seen the use of empirical rainfall threshold and the use of more complicated, let's say, prediction models. Both the top-down and bottom-up approaches are found to provide good performance in terms of prediction of and forecast of landslides. We have seen how satellite rainfall product outperforms, for instance, gauge data over India. And we have also seen the added value of the integration between the two different approaches. As I was saying, the obtained results will have a more important use in scarcely gauged regions, for instance, the developing countries, as they don't have a dense monitoring network. So satellite rainfall data can be very useful in that situation. And the combined use of satellite atmosphere and rainfall data for landslide guidance analysis show promising results. Thank you for your attention. Here you have my email address if you want to contact me about this topic. And here I have reported some of the reference I have cited within my presentation. Thank you again.